for trained least squares linear equalization. All right, this approach, it's called trained because we're going to assume that the receiver knows the signal values. And you might ask, well, what's the point of a communication system if the receiver knows the received signal values? Well, if you keep in mind, we often have some frame synchronization kind of steps that go with our communication system. So we know what those symbol values are. That's what we use to do frame synchronization. So we can use those same symbols that were used to mark the frames to train the equalizer. So it's not unreasonable to expect that you would have some training data periodically inserted into the communication stream. Okay, so we're going to do this with a matrix approach, and this is showing you the math on how this would work. I think in reality, most of the time you wouldn't want to do the matrix inversion that would come from this type of approach, but it gives you an idea of how you can use math to do the equalization process. There are lots of other techniques out there for doing equalization. We're not going to cover all those in great detail. Just like a lot of things in this course, we take a little bitty peek into some of the detailed math on how a communication system would work. And then we move on and we realize that in reality, things can be more complex or more sophisticated so that we get better results. Okay, so here's the idea. We're going to do an FIR, that stands for Finite Impulse Response. All those of you who've had DSP know about FIR filters. But if you haven't had DSP, that just means we have a finite number of terms in a digital filter. And so the equation of the filter is really simple. It's just the sum from j equals 0 to n. The filter taps is what they call those, or the filter coefficients. And then it's just the delayed versions of the received signal. So the output signal is just the convolution. This is the formula for convolution for FIR. The convolution of the filter coefficients with the received signal. Okay? We just talked about delay spread and how you would kind of be able to estimate what the order of this filter would be to handle a given delay spread. Okay, so the first thing I want to show you here is that you can actually think of filtering in this manner as a matrix operation. So I take a collection of the R's, right? So I started at Rn minus n plus 1, R of n, all the way back down to R of 1. And then I have this column vector of filter coefficients moving down this way, f0 through fn. So if I do this matrix multiplication, this would be R of n plus 1 times f0 plus R of n times f1 plus R of n minus 1 times f2, plus R of 1 times fn. Okay, so remember we've talked about this before, that when you do convolution like this, the indices line up. So here's an n plus 1 indice multiplied by 0. So n plus 1 plus 0 is n plus 1. Okay, and then n plus 1 is n plus 1. Okay, and so R of n minus 1 times f2, n minus 1 plus 2 would be n plus 1. So that gives you the filter coefficients, the filter equation by just doing this matrix multiply, this vector times this vector. Okay, so then you can start collecting all of these. Like here's y of n plus 1 right here, or y of n plus 2 is here, y of n plus 3 is here. Collect those into this column here, and you would have a matrix R times this vector F. All right, so in matrix form, it's y equals R, where this is this Toeplitz matrix times F. Okay, all right, you don't really need to know anything about Toeplitz matrices, but it's just a common form of a matrix. All right, so y equals R times F. All right, next, what we need to do, if we're going to do equalization, we have to come up with a cost criterion. All right, and so here's where this reliance on the parameter delta shows up. All right, he pushes this into the signal. All right, so he says, okay, we know that the signal is going to be delayed by delta. So we're saying S of k minus delta minus y of k, and if the delta lines up to match the physical delay in the system, then this is going to give us a smaller error, okay? So if we have our filter tuned right, we're trying to minimize this error. All right, so for a particular delta. All right, so this development from now on is going to assume that we have a certain delta. All right, and so we could make a collection of signal values and call that a matrix S. All right, so n plus 1 all the way down to S of p minus delta. Okay, so we have p values of the signal, right, and that would give us a collection of error terms that we could put into a matrix. All right. So for each sample time coming out of the system here, we have the signal and we can generate the error, all right, based on our filter that we're using. Okay, so in matrix form, this becomes pretty easy. E is equal to S minus Y, and Y is equal to R times F. All right, so it sounded really complicated, but it boiled down to something pretty easy in terms of matrices. That's why linear algebra is a required course in engineering curriculum. There's many times where you can boil things down into matrix operations. Okay, so from there, once we have something on the error, we can talk about a cost function. And our cost function in this case is just going to be to take a look at the squared error, add it all up, all right? And we're trying to obviously minimize that by choice of the filter taps, okay? And so because these are matrices, you can't just square it, but you can do, you probably did a little bit of this in linear algebra. E transpose times E, all right? That's sort of the matrix version of squaring. And we know what E is, so we can write that. And, I'm sorry, E transpose, and this would be E. All right, and so that can then expand. Not that you need to at this point, but you're looking at this matrix calculation to give you the cost function for a given choice of filter coefficients F. Okay? All right, well, from here, it's just a matter of, it's a matter of choosing F that minimizes, how would you find F to minimize the cost function? Okay, and so, I'm not needing you to understand every detail of this because after all, look at it, it's pretty messy looking. But you can work it backwards and verify this to yourself, all right? So the solution that he's showing you here is he defines this matrix psi, and here's this big long definition of psi, okay? It turns out that you can write the cost function as psi plus a bunch of other stuff, okay? So that's one thing you can do. In fact, I played around with this. You plug psi back into here, and you can show that this all boils back down to equation 13.12, all right? Now, I had to ask myself, is that worth it? Should I give that as a homework assignment? And ultimately, I decided not to, all right? If you're mathematically curious, you can plug that in. Otherwise, you can just take it on faith that the cost function turns out to be this parameter psi plus all this additional stuff. And when you look closely into the additional stuff, F doesn't show up, okay? So minimizing the cost function is equivalent to minimizing psi, all right? Now, heading back towards psi, if when I look at this, I took enough linear algebra besides just what's required in undergraduate days to recognize that this looks like what we would call a quadratic form. All right, and so one of the things about a quadratic form is that you know basically, if I had x minus x naught squared, all right, it's minimized at x equal x naught. All right, so I'm effectively having, let me erase this for a second so I can point to different things. I'm essentially looking at f minus something, and there's a thing in the middle that is like the scale constant. All right, so this is minimized when f is equal to this part, right? Let me get this going again. When f is equal to this, that's when we have the minimum. Okay, so that's what he mentions, that f is equal to this matrix operation. Okay, so depending on the length of everything, the order of the filter and so forth, here's a big inverse that you need to take, and there is, once upon a time, any inverse that was bigger than, say, 10 by 10 took a long time to compute, but we've gotten good with numerical methods, and we've gotten good with computational speed, so it's somewhat practical to do bigger matrix inversions, but of course, we're looking at optimizing power in a communication system. We don't want the little cell phone chip to be running all the time during these inversions. So practical algorithms are different. We don't use this matrix idea. We use some other things that are sort of closely related. All right, but this shows you how this all would work. All right, so that's the video that walks through the math on all of this. The next thing I wanted to show you before I leave this video is how would you handle this for different choices of delta. So basically his approach here is, this is one calculation for a given delta. All right, if you wanted to change delta, you go back here, recalculate everything for a different delta, do that matrix calculation again. Okay, and just loop through it that way. All right, well, it turns out you can kind of pile everything into one gigantic matrix. All right, and the idea here is that you know that delta, we don't know which delta to use, but we can put a range on it. Okay, so delta will fall in some range 0 to alpha. Okay, so 0 to alpha. All right, and so we could make this new matrix S bar that's a function of alpha. So effectively, we're putting in all of the choices of delta into this one S bar matrix and still forming the signal values in the same way that we did before. All right, and the same thing applies to the R matrix. We define the R matrix as the received values as a function of alpha. So alpha starts, R of alpha plus 1, you subtract 1 here, R of alpha, keep subtracting until you get R of alpha minus n plus 1. You build up this matrix. I'm going to show you this in MATLAB, and you get this R matrix. All right. Then you essentially have a collection of filters. All right. The row that you choose depends on what's the best delay term, delta. All right, so we go through this operation and we can calculate the optimal filter for each delta, and then we can calculate the cost function, the important part of the cost function, the phi, and just choose the lowest value that shows up on the diagonal. Okay, once I know the lowest diagonal value, because that's where the cost function is calculated, I can then select which of the filters works with the best delay time. Okay. All right, so I know that's a lot. We're going to walk through this example 13-1, a low order example of how these calculations work, and it'll give you a little bit better feel for how everything works out with this least squares matrix approach towards equalization.